All right, and I have audio, so it's a good day. Cool, awesome. My microphone shows up today, so we'll be rocking tomorrow. All right, so we're going to talk about cardinality today. We're going to move towards cardinality of infinite sets, and by the time we're done, hopefully you're going to wonder what the heck is going on in the universe, because there's some strange things out there, and this is one way to approach those. So I want to talk about a fable or a story about Hilbert's Grand Hotel. So anybody know who David Hilbert was? It's a good Google exercise. David Hilbert was a mathematician from the turn of the century, 1900s. Very prominent, trained a lot of other mathematicians. And one of the things he's famous for was in 1900 there was a conference where he posed a series of questions that he suggested mathematics should try to understand over the next 100 years. So they're called Hilbert's problems. And some of these have been solved, some of them haven't. Many of them have led to the development of entire areas of mathematics. Okay, these were just core problems that people started collectively putting their heads on, and sometimes led to very unexpected things. So Hilbert was a giant, okay? So that's the true part of the story. Now we go into the mythology part of the story. So the mythology is that Hilbert eventually got tired of mathematics, and he decided he wanted to do something different for a living. He decided to get into the hotel business. So he opens a hotel, and it's called Hilbert's Hotel. He didn't put the word grand in there. And people come to the hotel because they know David Hilbert's name, they were his students, and so on and so forth, and it's a very popular location for people to come and visit. Well, it's coming up to be Hilbert's birthday, and people decide they're going to throw a party at Hilbert's Hotel. And so the hotel books up. All the rooms are full. Now, originally, there were 20 rooms in the hotel, and each room has a door on the front, and the door has a room number on it. So there's room 1, there's room 2, and there's room 20. And the day of his party, all the rooms are filled up, so people have to stay in other hotels and so on. It's a good party anyway. Hilbert makes a lot of money over the next year. He says, you know what, I'm going to expand the hotel. I'm going to double its size. I'm going to add another 20 rooms. So he builds on until he's got rooms all the way up to room 40. And the next year there's another party, and the hotel fills up. Not quite as quickly, but it's, filled to capacity. He has another year, he makes more money. Well, this goes on for a number of years, and he starts making so much money, he just keeps adding on more and more rooms. And the hotel gets bigger and bigger and bigger, until eventually it has an infinite number of rooms. Okay, this is where people started calling it Hilbert's Grand Hotel, because it had an infinite number of rooms. Now, what does that mean? Each room still has a number on the front of the door, starting with 1, 2, 3. It means any positive integer that you think of, there's a room with that number on its door. Okay? 10,519,347,000,347. There's a room with that number on it. Okay? Any number you can think of, that's the sense in which it's an infinite number of rooms. So it's a really big hotel. So they're throwing a big party for Hilbert this year. And it turns out some physicists were reading their email out loud, right? One of them got the email and said, hey, I just got a cool email, there's a party coming up, and starts reading it at the same moment that somebody in the lab had opened a gateway to a parallel universe. And not just one parallel universe, but a bunch of parallel universes. So that there were an infinite number of people who found out about this party and wanted to come to this party. Okay, so we have an infinite number of guests coming to town to stay in Hilbert's Grand Hotel. And we're going to number these guests, guest 1, guest 2, guest 3, and so on. And again, infinite number of guests means if you pick any positive integer, there's a guest with that number. So the guests come to the hotel and they've received invitations and they have their guest number with them. So when they get to the front desk, they hand the clerk their invitation. The clerk says, oh, your guest number 743. You'll be staying in room 743. It's a very difficult job. And they go down to room 743 and they've got their accommodations. Okay, so it's party time. It's 8 p.m. The party's starting. Every guest has arrived. Every room has a guest in it. Every guest has a room. Nobody's doubling up. None of the rooms are empty. Okay, 100% occupancy. So every room is filled. It's one person per room. And everyone has a room. Thanks. All right, you got the setup. Infinite number of rooms, one guest in each room, nobody's doubled up, nobody is roomless, no room is empty. Okay, 100% occupancy. Now it turns out there was an old grad student of Hilberts who had heard about this party, hadn't gotten an invitation, but was in the area and thought, hey, I'm going to go to this party. I'm going to see if I can get a room at the hotel. Had some car troubles, had to wait for a repair, comes in about 11 o'clock at night and goes to the front desk and says, you know, I'm a former student of David Hilberts. I'd really like to find a room in your hotel. Is there any way you can fit me in? And the desk clerk says, yes, I can do that. And he pushes a button under the table and he hands this new guest a key and says, here's your room, enjoy your stay. So here's the first question. The rooms were 100% full. How did the clerk manage to squeeze one more guest into the hotel if every room was already occupied? So this is one of the questions of the Grand Hotel. Every room filled, infinite number of rooms, infinite number of guests. New guest arrives. How do you find space for them without doubling up, without kicking somebody onto the street? Yeah.
I've heard this before, so I don't remember the thing, but I think you can have everybody move to the room their number +1.
All right.
And then room 1 would do it.
There's a good strategy. You push that little button under the desk and it lights up a sign in each room that says, sorry for the inconvenience, please move to the room immediately adjacent to you. And so the person in room 1 moves to room 2, the person in room 2 moves to room 3, and so on, which leaves room 1 empty, and your new guest can go into room 1. Does that work? It must. Because every room has a room to the right. If there was a room that had no room to the right, that would be the largest numbered room. And we could pick any number larger than that room's number, and there'd be no room with that number. Since there's an infinite number of rooms, whatever room you look at, there's always another door to the right. And so everybody can get up at the same time and move one door over, and room 1 is empty. So even though the rooms were completely filled, we can still find more space somehow. Okay, that's the first weird thing. And clearly, if another guest shows up late, the clerk can repeat this trick, and you can squeeze a second guest in, and you can squeeze a third guest in. So however many guests you have showing up, one at a time, you can always find room for them in the hotel. Well, the room's full. The party is in swing. unfortunately, Hilbert actually had two grand hotels, both with an infinite number of rooms, and half the guests actually went to the wrong hotel. So across town there's another hotel with an infinite number of guests, and about midnight they realized there's really no party happening here, maybe it was the other hotel. And someone goes out and checks and they come back and they say, yeah, it's over at the first hotel. So now you have an infinite number of people coming to this new hotel, and they all come up to the clerk and they say, we'd all like rooms. Is there any way you can fit us? And the clerk says, sure, no problem. Presses another button and hands everybody their keys, and they all go in and everybody's got a room. So how can you squeeze an infinite number of new guests into this hotel when every room is already occupied?
You have each guest move to the right an infinite number of times?
That would take an infinite amount of time. Right idea, though. Yeah.
Tell every guest if you're in room N, go to room 2N.
There you go. Have every guest from room N move to room 2N. So guest 1 goes to 2, 2 goes to 4, 3 goes to 6. And when you do that, all of the odd numbered rooms are free. So you free up an infinite number of rooms, and now you can put your infinite number of guests into there. And it's kind of like having everybody move an infinite number of rooms, but everybody's moving a finite number of rooms. But some of the guests have to move really far. Guest 1 billion has to move 1 billion rooms down, right? But it's always a finite number of rooms. So an infinite number of new guests, you can still fit them in the hotel. So this is truly a grand hotel, right? And certainly if another infinite busload of guests come up, you can fit them in by doing the same thing. All right. Well, there's another hotel in town. This is called Blauman's Not So Grand Hotel. And in Blauman's hotel, the doors have real numbers on them. And all the numbers are between 0 and 10. But the room numbers are real numbers. And Blauman's hotel is completely filled up with guests. And they find out about this party, and all the guests from there come over to Hilbert's hotel, and they go to the clerk and they say, we'd like a room. And the clerk says, sorry, I can't do that, there's too many of you. Because even though you can fit an infinite number of new guests in, if those guests come from a hotel where the rooms have real numbers from 0 to 10 and every room is occupied, that's too many guests. You can't squeeze them into this infinite number of rooms. So there's clearly something fishy going on here, right? There's clearly some notion of infinite, really, really infinite, too big infinite to fit in this infinite. So there are sizes to infinity. Saying there's an infinite number of something doesn't tell you how big it is, because in some cases it's an infinite that can somehow squeeze in more infinites, and in some cases it's too big. So this is the sense in which we want to think about cardinality. Cardinality, again, for a finite set is just the number of things in the set, but it's a different thing for an infinite set. So for an infinite set, set A, we use the same symbol. A, absolute value symbol, is the cardinality of A. Somehow measures the size. So it's grasping somehow how much stuff is in there, but we already know it's got an infinite amount of stuff, but we want something more detailed than just an infinite amount. So let's define equality of cardinality. So cardinality of A equals cardinality of B if and only if there exists a function from A to B which is injective and surjective. So we got to remember what these definitions mean. Injective means one-to-one. Injective means two different things here will map to different things over here. Surjective means everything over here gets mapped to. So we can call this bijective sometimes. So, well, let's stick with positive numbers. So positive integers p. And let A be the set of positive even numbers. We can define a function f from the set of positives to the set of positive even numbers by just saying f of x is equal to 2x. So we take any positive number, we multiply by 2, we get a positive even. Is this injective? If we have two numbers that map to the same value 2x, are those two numbers equal to each other? Sure. The only time 2x equals 2y is if x equals y. So it's injective and it's surjective, right? Every even number is twice some positive integer, every positive even number. So this is a bijective map, and because we have that bijection from P to A, we can say these have the same cardinality. And we could do the same thing with a little twist with odd numbers. And we don't just need positives, we can do this for all integers. So the cardinality of the integers, the cardinality of the evens, the cardinality of the odds are all the same. And that's why we can do this trick at Hilbert's Hotel. Let's look at a similar case. So let A be the set of positive integers, that's the door numbers, right? Let B be the set of positive integers bigger than or equal to 2, right? Is there a one-to-one mapping between this set A and this set B? Absolutely. We can say f goes from A to B, f of x is x plus 1. Okay, that's the function that the clerk used to move guests so that they could make space for a new guest. Each guest moved from room x to room x plus 1. And this set has the same cardinality as this set because we have that bijective map. But if our set of rooms that are occupied is this set, right, room 1 is unoccupied. That's how we had room for another guest. So lots of things have the same cardinality as the integers. Okay, the set of prime numbers has the same cardinality as the integers. And let's do a little bit of mechanical work. cardinality of primes equals the cardinality of the positive integers. Can you think of a way to find this one-to-one mapping from the positive integers to the set of prime numbers?
You could just say that the first function maps 1 to 1, and then 2 to 2, but then 3 to 5. Do it manually, kind of.
Okay,
That would
so
be
we're
fine.
mapping we're defining this function f from positive numbers to the set of primes.
Has anyone ever proved that there's an infinite number of primes?
Yes, and we will too.
Okay.
We'll prove that in a few weeks. So we can map f of 1 to, well, how about the first prime? And f of 2, how about the second prime? And f of n, how about the nth prime? Is that a well-defined mapping?
I'd say so.
Right? Each number goes to exactly one value over here. Every value over here, every positive integer maps to some prime if we believe there's an infinite number of primes. Every prime has something mapping to it, and different numbers map to different primes. So there's a bijective mapping. And that's all we need to say the cardinality of this set is the same as the cardinality of that set. But what did we do? We counted the primes. We took the elements of this set and we somehow said, okay, this is the first element, this is the second element, this is the third element. As long as we can do that and we hit every single element, we can find this mapping. Map 1 to whatever the first element was, 2 to the second, 3 to the third, and so on. So anything that we can count has the same cardinality as a set of positive numbers. And so we actually call this countably infinite. And countably infinite means the cardinality is the same as the cardinality of the positive integers. So being able to count things, which basically means being able to put them in some order, is all we need to be able to say this thing has cardinality of positive integers. Okay, what about the set of all integers? What if we move beyond just the positives? Well, let me write the set of integers like this. Right, it's the same set because the order doesn't matter. But what I've done is I've ordered these things in a way that I can say this is the first integer, this is the second, this is the third, and so on. I can count my integers like this. If I want to know what the 8th integer is, it's 1, 2, 3, 4, 5, 6, 7, 8 is the number 4. And again, every integer appears in this set exactly once. So this shows that the cardinality of the positives is the same as the cardinality of the integers. And that's actually what we are thinking of when we talk about a set being countably infinite. Cardinality of the integers, but it's also the cardinality of the positives, or the primes, or the evens, or the numbers that are perfect squares of integers, or any other thing. All right, so this is kind of a magic number, and we have a symbol for it, which is Aleph-naught. It looks much cooler if someone who actually knows how to write that draws it, but that's my best version of it. So Aleph-naught, or Aleph-null. All right, well, lots of things have the cardinality of the integers, right? What about rational numbers? What about fractions? So the set of all integer divided by integers, which is somehow an infinite number of an infinite number of things, right? We know if we take two copies of the integers and we put them together somehow, it's still going to be the same cardinality, right? Doubling the number of things doesn't somehow make it more than Aleph-naught, because you have an infinite number of evens. If you double that, you get the set of all integers. It's still Aleph-naught. So doubling the number of integers, right, if we write an integer in green and we write an integer in blue, that set still has the same cardinality. But if we think about rational numbers, fractions, right, the numerator can be any of an infinite number of things, the denominator can be any of an infinite number of things. It's kind of like infinity times infinity almost. So what's your guess for the cardinality of the rational numbers? Aleph-naught or bigger than Aleph-naught? Just gut feeling, how many think it's the same as the integers? How many think it might be bigger? That would be my guess. So how can we figure this out? Well, let's make a matrix. And we're going to represent the number p over q. And I'm going to list integers across the top. And what I'm going to do is at each point in this matrix, I'm going to fill in the value of p over q. So this is going to be 1 over 1, this is going to be 2 over 1, 3 over 1, 4 over 1, and so on. This is going to be 1 over 2, 2 over 2, 3 over 2, and so on. This is going to be 3 over 4, this is going to be 5 over 5, this is going to be 6 over 7. And if we're just thinking about positive rational numbers, does every positive rational number appear somewhere in this matrix, assuming that we continue out through all integers? Every rational number has to be written as writable as p over q, where p is some integer and q is some integer. So if I move over to column p and I come down to row q, I'm going to find p over q there. So this table contains every rational number. And it actually contains more than that because, for example, 5 over 5 and 2 over 2 and 1 over 1 are all the same value. So the set of things in this table is bigger than the set of rationals. So if I could show that the set of things in this table was countable, had the cardinality of the integers, then certainly the set of rationals would also have the cardinality of the integers, because it's a smaller set. So to show that something's countable, all we have to do is order the things in that set. Well, here's an ordering we can impose. We're going to start here, we're going to move over, we're going to come down a diagonal, and then come down, and then go up a diagonal, move over, and then come down a diagonal, move down, go up a diagonal, move over, and if we keep doing this, we get a pattern like this. And so on. If I continue drawing this pattern, do I eventually hit every single square? Let me rephrase that. Is there any square which is never hit by this pattern? No. I'm not going to hit every single square unless I draw this an infinite length, right? But any p over q that you pick, it might be way over there and way down there by that other building. But eventually this line will go through that point. And so my mapping is 1 maps to this, 2 maps to this, 3 maps to this, 4, 5, 6, 7, 8, 9. And there's a mapping from the set of positive numbers to the set of rational numbers. And since we have this bijective 1-to-1 mapping, their cardinality is the same. And that's again the cardinality of the integers. So the set of rational numbers is also countable. Right, you can put it into 1-to-1 correspondence with the set of integers. So now you got to start to wonder, is there anything that's bigger than the integers? Is there any set that has so much stuff we can't put it into 1-to-1 correspondence with the integers? The what? Irrational numbers, more simply real numbers. But we'll come back to irrationals. So real numbers, remember when the guests from Blauman's Hotel with real number doors came over, the clerk couldn't fit them in. That's because the cardinality of the reals is bigger than the cardinality of the integers. And since rationals have the cardinality of the integers, if we subtract out the rationals, we get the irrationals. That's going to have bigger cardinality also. But I'm going to work with reals because they're a little simpler. So the reals have a bigger cardinality than the integers. How in the heck would you prove that? Because it's one thing to find a mapping, to say, hey, if I number my things like this, I can make this clever red line, there's a mapping, so the cardinalities are equal. But how do you prove that there is no possible mapping? Right? That's a much harder undertaking.
I was going to say, I know a way that you prove that you couldn't, because you can't ever reach that point to 0 and get times 1.
I could map 1 to that.
But I mean, you could by saying there's infinite zeros, but then how would you say, and then you add 1 to that,
Mm-hmm.
you again. Okay, but then you could say if you do that, then you'll never reach 1.0.
Right. But you can do some mappings, right? Like I could say f of 1 is 0.1, f of 2 is 0.11, f of 3 is 0.111, and so on. And so any number in this form I've mapped to from a positive integer. Well, I could come up with another mapping that maps to, 0.21, 0.22, 0.23, and make that set countable, and I can put those together and it's still countable. But it's hard to imagine how to construct a function that maps from the reals, maps from the integers to the reals, right? Because of this problem that you're describing. But not being clever enough to come up with an answer doesn't mean there is no answer, right? That's the trick of mathematical proofs. I've thought about it, I can't figure out a function, I guess one doesn't exist, doesn't work. But it is possible to prove that this is true.
The set of integers is a subset of the reals, right?
Correct.
And there are an infinite number, an infinite quantity of real numbers between each integer and a set of real numbers.
This is also true.
So then, could you say that for each integer in the set of real numbers, there's an infinite number of other real numbers that are not integers,
Mm-hmm.
and somehow work with that?
You could, but here's the problem. Between 1 and 2, there's an infinite number of rational numbers. And in fact, between any two rational numbers, no matter how close they are, there's an infinite number of rational numbers. So we have this weird kind of like nested doll effect going where we've got, infinities inside infinities, an infinite number of times, but yet the rationals are still countable. So even though that feels like it would be fundamentally bigger, we're not going to be able to use that to get into a proof of this because that's also applicable to the rationals. So this is weird stuff, right? I mean, infinities are definitely oddballs. But let me show you a simple way to prove this. Simple once you know it. I don't know how the heck someone came up with this originally. we'll do a proof by contradiction. So suppose F is a map from, we'll just go from the positives to, let's just go to a subset of the reals. Let's just go to the things between 0 and 1, right? If you can show that this has the same cardinality as P, we can jump up and down and be happy, right? Because this has cardinality bigger than the cardinality of the integers. So let's suppose that that's not the case. Suppose there is a one-to-one mapping here. So suppose F goes from P to 0, 1 is a bijective map, right? Meaning that every element over here gets mapped to from some integer. Okay, well, let's write out what these mappings might be. So F of 1 might be 0.2473160000. And F of 2 might be the fractional part of pi. And F of 3 might be 1/2. And F of 4 might be 1/3. Okay, whatever that function is, we could fill out this table and say, you know, this is what F of 1 is, this is what F of 2 is, and so on and so forth. Now we do something really evil. F of 1, we look at the first character after the decimal point. And we add 1 to it. F of 2, we look at the second character after the decimal point, and we add 1 to it. F of 3, we look at the third character after the decimal point, and we add 1 to it. F of 4, we look at the fourth character, and we add 1. And if it's a 9, we're going to change it into a 0. And we keep doing this. And what do we get? We come up with a number. And I'm going to call this number x. So let x be this number that we construct in this way. It's going to have an infinite number of digits. It's going to be a real number. It's going to be between 0 and 1. Therefore, there must be some f, some n, which maps to x. Because we're claiming that f maps to everything between 0 and 1. But this is impossible. Because when I construct this number, the nth digit is going to differ from f of n. The nth digit of x will be the nth digit of f of n plus 1, which means it cannot be equal to x. So, but f of n's nth digit is not equal to x's nth digit. Therefore, f of n is not equal to x. And there's your contradiction. Since we reached a contradiction, therefore f does not exist. Therefore, the cardinality of the positives is bigger than the cardinality of this tiny little interval of real numbers.
Isn't it the other way around?
You're right. Thank you. All right, so this is sometimes called Cantor's diagonalization. Diagonalization is a general technique, and it's named because you're going along the diagonal here and you're doing something. And you're kind of setting yourself up for success and then deliberately throwing in a little monkey wrench that just like twists things around so that it's impossible to succeed. That's, to me, how a diagonalization proof generally feels. And these things pop up in philosophy. They've popped up in some of my computer science research that I've been doing. they're kind of weird and quirky. But that's a sufficient proof that not everything has the same cardinality as the integers. So the cardinality of the reals is strictly bigger. You've got to say hence when you're doing math. Hence, the cardinality of the reals is bigger than the cardinality of the integers. Pretty weird. All right, let's take this one step further. This is not like final exam material, by the way. Okay, this is just kind of knowing this stuff is out there. I want you to know the cardinality of a finite set is the number of elements. I want you to know that the integers have cardinality Aleph-naught, and the reals have bigger cardinality. But that's all you need to know about this. Okay, you don't need to know about Hilbert's hotel and so on. So we can start looking at orders of infinity, and we can start making a category. Finite sets have cardinality, which is some integer number, and then there's the integers, which has larger cardinality, and then somewhere over here there's the cardinality of the reals. But here's a question: is there some set with cardinality in between these two sets? So is there a set C such that cardinality of the reals is strictly bigger than the cardinality of C, which is strictly bigger than the cardinality of the integers? We already know the cardinality of the reals is bigger than that of the integers, but is there a set in between? Or is it possible that as soon as something is bigger than the integers, it's at least as big as the reals? So we start with the integers, we add a few elements, it's still the integers. We add more elements, we add an infinite number of elements, we add the rational numbers, and it's all just the cardinality of Z. When we toss in the irrationals, suddenly we jump over to here. So is there a set whose cardinality lies in between those two? So this is a famous puzzle. And it's got a name. It's called the Continuum Hypothesis. And the Continuum Hypothesis basically says this: if the cardinality of some set C is bigger than the cardinality of the integers, then it's at least as big as the reals. So if the Continuum Hypothesis is true, any set that's bigger than the integers is at least as big as the reals. If the Continuum Hypothesis is false, it means that there's some set that's bigger than the integers, but not bigger than the reals, not equal to the reals. There's something in between there. And nobody has ever proven or disproven the Continuum Hypothesis. So we'll do it by vote. So raise your hand if you think the Continuum Hypothesis is true, if you think there's nothing between the integers and the reals. Just one person? All the prize money goes to one person. Two people, you can split the prize money. Okay, raise your hand if you think the Continuum Hypothesis is false. More ways to split the prize money. All right. If you voted for this being true, you are not wrong. If you voted for this being false, you are also not wrong. It turns out that you can neither prove nor disprove the Continuum Hypothesis. It's what's called formally undecidable. And it's been proven that you cannot prove CH, and it's been proven that you cannot disprove CH. There's no way to either prove or disprove this hypothesis in our system of mathematics. And I didn't say we don't know how to prove or disprove. It's been proven that it is impossible to prove this, and it is impossible to disprove it. It's a third case that's called undecidable. And it's been proven that CH is undecidable in our system of mathematics. And that should worry you somewhat. Because we live in a world, we experience the universe in a way where things are either true or false, right? This may be the case or it may not be the case. CH does not fall into that category. It could be true, it could be false. In either case, it seemingly has no effect on any proof or counterexample we might try to develop. So that's a little weird, and that can throw a monkey wrench into your philosophy, into your logic, into your mathematics, into your theology, into your sociology, into all kinds of things. And this is the tip of the iceberg. So in the 30s, Kurt Gödel, a relatively unknown mathematician, delivered a paper at a pretty small conference where he basically proved that in any system of mathematics you develop, you're always going to find theorems that you can neither prove nor disprove. And it really kind of shakes your whole foundation of what mathematics is. Because if you start with your axioms, you should be able to prove everything. And he showed that if you add enough stuff so that you can prove everything, you introduce contradictions, paradoxes. And if you make your system consistent so there are no paradoxes, there will always be statements you can neither prove nor disprove. And that's something today we call the Incompleteness Theorem. So all good stuff to Google if you're intrigued by any of this and you don't have any homework coming up.
Was the incompleteness theorem, was that kind of saying that we're never going to stop moving things in mathematics?
I don't know if that comes from it.
Because, I don't know, what that says to me would be that if the only answer to having contradictions by completing more things would be, or by finding more ways of solving the problems would be to continually, is that our basis of our information is never complete.
That could be an interpretation of it. I don't know if it's possible to discover everything there is that can be discovered in a system and then see that there's gaps there. It's an interesting question.
So in my mind, yeah, you can never discover everything there is in a system, whatever it is.
Yeah. And I have a copy of Gödel's original proof in my office if anybody's really interested and you don't want to look it up. All right, so so tomorrow we'll come back down a little bit and we'll talk about some more things related to functions and sets and sequences. I will post your next homework by tonight to work on, and we'll talk about this current homework set tomorrow. All right, I'll see you then.